Okay, welcome back, everyone. We were talking about not the less traveled path, but the more frequently traveled path of dark matter in these lectures. And in the last lecture, I told you about the evidence for dark matter. This is incontrovertible. There's no controversy about that. I even talked a little bit about MOND. Before we start today's lecture, where I will mainly focus on cosmological probes of dark matter. So cosmology essentially gives us information about two things about dark matter. One is how much of it is there, and the second is how is it distributed, in the visible universe. These are the two things, and these two pieces of information are already very useful to tell us something about the nature of dark matter. We will see that. But before we get to that, I have to make a couple of corrections from yesterday's lecture. So let me go over them one after the other. The first is um, when we discussed rotation curves of galaxies, somebody asked a question: which reference frame are these speeds plotted in? My answer was wrong. I said from the reference frame of the Earth. The answer is no. It has to be, of course, the reference frame of the center of the galaxy for which the rotation curve is being plotted. That's obvious, right? I mean, so we can look at it. What is happening is that there is some galaxy like this, and you are here. This is Earth, and there are stars that are going this way. There are stars that are coming this way. For these stars which are going away, you are going to see a red shift, red Doppler shift. For these ones, you might see a little bit of a blue Doppler shift, except of course that there is also a relative velocity between the Earth and the galaxy that you're observing. So in principle, everything could be redshifting because let's say this other galaxy is moving further away. In the case of, let's say Andromeda, the whole galaxy is coming towards us. So although we would like to plot these velocities of these stars in this other galaxy in the frame of the center of the other galaxy, that is not a quantity that is accessible to us. So what we can do, we can measure the Doppler shifts as they are from the Earth reference frame, but separately we can somehow measure the relative velocity between, let's say, the Andromeda galaxy and us. And then we subtract out that velocity. So we would say that we observed in the, let's say, direction of like line of sight minus the V known relative, known relative. This is equal to V circular, which is being then fed into this equation, which is what is then being plotted. So this was the first correction. Thank you to Professor Piyush Bhattacharya who pointed out this mistake yesterday. So I did mean, of course, to say this, but my actual answer was completely wrong. Thank you to him for that. Okay, the second thing is a minor typo. So when I discussed gravitational lensing, everything is fine here, except that I put in this factor of 4 by hand at the end, saying that in GR you get a factor of 4. The factor of 4 is in the wrong place. It should be in the numerator. Okay. Okay. So this is what I wanted to correct. And I just wanted to draw your attention to one more thing, which is we talked about MOND, okay, where the F equal to ma log gets changed, and I showed you, F is equal to ma becomes F times ma square by some new constant called a naught for small accelerations. Everything is fine here, there's no correction, but one thing I forgot to mention is that note that this makes the equation nonlinear, because this equation F is ma square, if I write it properly in the notation that we are more familiar with, F is m dx d square x by dt square. Then on top of that, I have to do a square times 1 over a naught. Now this is a very weird equation, right? So what we, where the second derivative comes squared in the equation. So this is just something to be, something to be aware of. For example, if you rewrote it as d2x dt square, let's say 1 over root a naught is equal to square root f by m, you can see that the forces do not add properly now. If you want to, so just addition of two forces does not lead to linear addition of the accelerations. So this is a very weird equation, just something to remember. Okay, so now we can go back to today's lecture. But before that, any questions about yesterday's lecture or the corrections that I just mentioned? Any questions at this point? I don't hear anything. All right, so now this is lecture 2. Today, we tackle a different problem. So we know that there is dark matter. Now the job is to find out what is it made of. And this is a very interesting problem because on one hand, we are looking out there in space and we found something new. And we don't know what it is, but the job of finding out what is the world made of has typically been the job of particle physicists. But now suddenly the astrophysicists or the astronomers need the help of particle physicists. And the particle physicists, they have been doing experiments in their labs and with these colliders and everything. We are also finding that looking at space gives us new opportunities to discover the fundamental nature of what this world is made of. So it's a very nice coming together of two communities. It's presented as a clash of worldviews in this comic, but I rather think of it as a very beautiful opportunity to do very interesting kind of physics. So I want to start with a story, a parable, if you will. So imagine that you are in, the time where we don't know all the elements of the periodic table. We know there is something called oxygen. Lavoisier has just discovered oxygen in the lab. He's created it. We know that it burns when you put some, let's say when you put some, let's say, coal in some big blob of, in some bottle of oxygen. You can burn the oxygen away and all that. And people have figured out that there is something called nitrogen because there's something called azote and nitrogen can be created in some chemical reaction. So we know that, okay, air is mostly made of nitrogen and oxygen. At this point, Lord Rayleigh does an interesting experiment. He shows that the nitrogen that you extract from air, you take a bottle of atmospheric air and you burn out the oxygen out of it, or you somehow extract out the oxygen. So you're supposed to be left with mostly nitrogen. This nitrogen he found was heavier than the nitrogen that he could synthesize in the lab from chemical reactions. So in some sense, this is also a mass discrepancy problem, right? That what nitrogen that I create is not as massive as nitrogen that's out there in space. So there is clearly something called dark air, which is out there, which I am not detecting and I'm not aware of. Now, from this discrepancy, he figured out that what was there in air other than nitrogen was a little bit more of a new unknown gas called argon. And this argon gas is heavier, and that's what makes the nitrogen from air heavier. The funny thing is that even before all of this discovery happened, there were others, spectroscopists, who had done spectroscopy of air, and they had seen unexplained lines in this air, which correspond to argon. Of course, argon is a inert gas, but at sufficient temperature, you can excite it and you will get spectroscopic lines. So you see, there are three ways of studying gases, if you will. Either you can do thermodynamics, which involves things like PV is equal to, NRT kind of equations, where you make no reference to what the gas is made of. There is no reference. In the equation PV is equal to nRT, essentially there is no information about what makes up the gas. There is the complete other extreme where you need to know the full atomic structure of what makes up the gas. In the case of argon, you'll have to tell me how many electrons are there, how many protons and neutrons are there, and then I will be able to tell you what are the energy levels and everything. But there is a middle path. The middle path is one of kinetic theory, where you can do certain experiments where, let's say, you take this box of gas and you make it expand adiabatically. And then PV to the power gamma is constant. And this constant gamma carries some information about whether the gas is monoatomic or diatomic. You can look for diffusion of this gas or effusion of this gas. Take a box, make a little hole in it, and see how fast this gas comes out. This gives you a measurement of the mass of the individual particles that make up the gas. So kinetic theory is somewhere in between. It is not as blind to the microscopic description of matter as thermodynamics is, which is why thermodynamics is powerful, by the way. And it is not as detailed as chemistry is. However, each of these three methods has its advantages. Thermodynamics is very useful because you don't need to know any microscopic details and you still know certain results very, very solidly. Chemistry is great because you figure out lots of very detailed properties which you would otherwise never find. But each of these two methods has its disadvantages. Thermodynamics cannot give you details. Chemistry cannot be done until you know the details. So the thing that connects these two approaches is kinetic theory. This same philosophy needs to be applied in the case of dark matter. We know that there is dark matter. We know that there is some total amount of dark matter in the universe. In the lab, particle physicists are trying to figure out what exactly are the interactions of dark matter. You're trying to write down some Lagrangian. You can try to write down some very complicated model. But you see, these two are very far removed from each other. There is the necessity for an intermediate approach. And that intermediate approach is what I will focus on today. Very model independent, as far as possible model independent, but still getting some information about the nature of the particles that make up this gas of dark matter in the universe. So this is the philosophy. Okay. All right. So a couple of references. So of course, everyone knows about Kolbe and Turner. This is the Bible of astroparticle physics. Dodelson for anything to do with cosmology, in particular, I would say structure formation, CMB. And there's a very nice introductory book by Stefano Profumo, who also is a speaker in this workshop. So you should all listen to him. It's a very beautiful book with lots of very beautiful jokes. I like the book very much. For understanding details of thermodynamics in the expanding universe, there is an old book by Bernstein. Not many people have seen it, but I like that book very much. You can take a look at it. I also would like to draw your attention to a couple of specific notes and papers. So there are some notes by myself, Asim Paranjape and Shubhendra Mohanty, based on a course that we taught last year during about the same time in Pune in the Search School. Those notes might be useful. Bauer and Plane, this is a fantastic set of notes. If you really want to study by yourself, from the slightly particle physics point of view, you want to understand dark matter, there is no better place to start. Just download Bauer and Plane from Tillman Plane's website and just go through it, cover to cover. It's a beautiful set of notes, highly recommended, highly recommended. And for freeze out, because it's such an important topic, thermal freeze out, there are many treatments, but I hope I am not being very modest when I say that you should go and read this paper. I am a co-author, where we really explain how this thermal freeze-out calculation should really be done. Um, the part that we focus on is how to solve the equation. There's a second technicality in that, which is how to define something called average sigma v. For that, of course, you can look at the previous very nice paper by Gelbini and Gondolo. Okay, so these are references. So let's begin. Okay, cosmological probes of dark matter. So there are essentially two observables in cosmology that really probe the nature of dark matter. One is cosmic microwave background. I told you yesterday already about the fluctuations of the cosmic microwave background. The second thing that probes the nature of dark matter in cosmology is the structure at large scales, actually even at moderately large, small scales even, but how dark matter is distributed in the universe. These two things, so here, for example, in these two maps, if you will, one is showing the fluctuations of temperature in the universe, and then we will tell you how to go from this picture of fluctuations of temperature to something like a correlation function, which is what is plotted here. And similarly, you could do this with, let's say, positions of galaxies, that you have lots of galaxies all over the universe, and you're looking at them, and you find out what is the 2-point correlation function of galaxies, and that information is represented in this power spectrum. I'll tell you more about this as we go along. These two, sorry, these two pieces of information or observables give us a lot of insight into the nature of dark matter, both about its abundance and about its particle nature. So that's what we will discuss in the next, let's say, 45 minutes or so. Okay, so the abundance we all know. I hope everyone here is familiar with these notation. We know that omega h square is something like 0.12. Omega, we know what the definition is. It's basically something like rho by some rho critical, something like this. So we know that how much of dark matter is there, and this sort of a map, when you take the 2-point, it tells you that there is this power spectrum, and it tells you that, okay, the power spectrum looks something like this. So these are, and we also know these slopes pretty well. These are very well explained. So the position of the peak and the slopes on either side, very well, determined by data, and actually very easily explained using dark matter. So we'll go over that. So as I said, the first thing that we want to talk about is abundance, and then the second half will be talking about how it is clumped and how each of these things tell us something about the nature of dark matter. Okay. So the first idea is that, so okay, we want to explain why omega h square is 0.12. Okay. So the first idea that very nicely explains this number is something called thermal freeze-out. Many of you are familiar with it, but it's just revision for you. Very early in the universe, everything is at equilibrium at this high temperature, and dark matter, let's say I represent it by some particle called X, can annihilate, let's say, into a pair of standard model particles, and conversely, two standard model particles can kill each other, particle-antiparticle, and make dark matter pair. And both of these reactions are happening equally fast, and so everything is in equilibrium. The universe is expanding, and you should think of this circular blob that I'm drawing as one co-moving volume. Okay, one co-moving volume of what size I will tell you later. It's some co-moving volume. As the temperature drops below the mass of the dark matter particle, the standard model annihilations will not give the dark matter particle in the final state, because that is Boltzmann suppressed. whereas dark matter annihilations can continue. As a result, relatively speaking, the dark matter abundance is going to drop. Now, if this continued forever, we would just get rid of all dark matter. Okay. But what happens is very interesting. The universe creates a non-equilibrium condition. The universe is continuing to expand, and then it expands to such a level that the density of dark matter becomes very low, and in one, let's say, in the co-moving volume correspond to, let's say, one of its mean free path, it does not find another dark matter particle. So there is no partner with which it can annihilate with. So then this particle is left alone forever, and it is what we would call is the relic density of dark matter. So this is the heuristic picture of how dark matter can be left behind as a relic of a thermal evolution of the universe. This is called chemical freeze-out. Okay, because the chemical reaction, chemical means number changing reaction of dark matter annihilations, they freeze out at some particular temperature. Okay. Now this we want to understand in a little bit more detail. There are two ways of doing it. One which is a little bit simpler and gives the correct idea, and then one which is a little bit more rigorous. Let me do the simple one first. The idea is the following, that early in the universe, so let's say this is time and this is number density. Now you see, number density would by itself reduce in the universe because the universe is expanding. So let's divide the number density by the scale factor q, because then now this guarantees that if nothing is happening, this quantity is going to stay constant. Okay, so very early in the universe, this quantity stays constant. Okay, now once the time is such that the temperature becomes roughly the dark matter mass, this starts falling exponentially because of the e to the power minus m by t in the number density of dark matter. At some point, then, the reaction rate gamma becomes smaller than the Hubble rate, and after which there are no further interactions. So we would say that this freezes. So we expect this to happen, whereas if it was always in equilibrium, it would probably do something like this. It would keep decreasing exponentially. Instead, it freezes out. So one way to therefore compute the relic density, this relic density of dark matter, would be to say that, well, dark matter followed the equilibrium curve until the point that gamma became equal to h, and after that, whatever the density was there, that is the thing that leads to the relic density of dark matter.
Basudeb, just one comment from Raghu. I think you are plotting n times a cube, or
yes.
Yeah.
So, yeah. Typo.
Yeah. No.
Thanks. Good. So this is the rough idea. We can make this a little bit more precise. So let's. Okay. This also gives us a chance to revise one very general idea, which is in any interesting calculation involving cosmology, it boils down to a competition of rates. Okay. So gamma is a rate. It has units of 1/time. Hubble is a rate, and this comparison of rates is what gives you all interesting behavior. So let's see how to do this calculation in some ways. So first of all, let's see what is gamma. Gamma is n cross-section relative velocity. For relativistic particles, n goes as t cube. For non-relativistic particles, you can write down the Boltzmann form and Maxwell-Boltzmann form. Sigma is interesting. Let's write down sigma. Sigma sigma has units of length square. So therefore 1 over energy square. So at high temperatures where everything is massless, relatively speaking, sigma must go as T square, for T much larger than all masses. Whereas at low temperatures, it must go as the mediator mass to the power 4, because m square appears in the propagator, and then amplitude squared will give me cross section. And then I need, something on the top. So what I need is, let's say, this should be 1 over T square. 1 over energy square is length square. And here I have the mass square divided by the mediator mass square for T. Okay, so this is the form. N, let's say, for now, let's just say that N goes as T cube. Let's just say that for now. And V, let's just set it to 1 for now. So you will find that N sigma V goes as T for large T. Okay. And say m square T cube over m to the power 4. Of course, I can't really use it at large T because now this T cube is perhaps not quite right. But let's just write it for now. So if you then plot H goes as T square by m Planck. So gamma by H, this ratio, this as a function of time, if you see at early times, gamma by H goes as 1 over T. And at late times, it goes as T. So it has a peak. Okay. So this roughly is the time at which most of the production happens. Now, for some particular interactions, it may so happen that the peak is so early on that you are only seeing this part of the behavior. But in general, it's good to keep in mind that gamma by H has this form. Okay. So now let's learn a little bit more about Boltzmann equations before we actually put in some numbers. But before we do that, if there are any questions, we can take them.
Basudeb, there is one question that I skipped from Raghu again. This is probably from what you discussed before. By clustering scale, can you clarify if you mean the size of the object or the distance between the collapsed objects? So this is.
So can you say that again?
By clustering scale, can you clarify if you mean the size of the object or the distance between collapsed objects?
Good. So the precise definition would be on what is the distance between two objects where there is the greatest probability of finding, two objects. So let's say I ask, object 1 is at origin, object 2 is at some distance d. What value of d makes it most probable that I will find, two particles at these distances? That's what I mean by, let's say, the correlation function. And the clustering scale, the length scale corresponds to this typical distance between particles, and the k corresponding to that is just 2 pi by this distance.
Okay. There is one more question pertinent to the present discussion from Suchetana Chatterjee. Is this specifically discussed in the context of dark matter?
Which one?
This probably relates to the relic abundance calculation. Is it, Suchetana?
Which one? Yeah, the
cross sections. Cross sections. Yeah. She means the cross section calculation. Is this specific to that?
So what I have used here is the fact that at early times you can treat, at high temperatures you can treat all particles as massless. So the only dimensional quantity that I have in the cross section is temperature. And in order to get a 1 over energy square, the only thing I can do is 1 over T square. Of course, there are coupling factors there. Something okay, or alpha square. And similarly here, whereas at low temperatures, masses become important, and this, of course, is model dependent. In the case of weak interactions, this is basically the Z boson mass. This is the dark matter mass. This is, of course, model dependent.
Okay, there is another question from Devash Sri. She's asking, just to follow Professor Raghu's question, does the scale you refer have anything to do with the correlation length?
The scale, it is exactly the correlation length. Except that correlation length is often used in the context of, let's say, power laws, where the 2-point correlation function goes as, say, power, some scale by some typical scale to the power some power or some exponential, where again you have to normalize. So that is what comes in there. Here, it's not exactly a power law. You will see that there are two powers. So I don't need to use that language, I suppose. But it is related, yes. It is related. Okay,
Okay, that's all.
let's go on. Okay, so the story is this. So the most important object, the object of interest when you want to do kinetic theory with dark matter, is its phase space distribution. Okay. This tells you, let's say, how many particles are there per unit volume d3x and per volume d3p. And I have what in mind something like, d3x, d3p, which is like h cube, the Planck cube. So this is the classical treatment, but you can also think of this as a Wigner transform of the density matrix coarse-grained over some de Broglie wavelength scale. Okay, so if it doesn't make sense to you, don't worry. It's just classical. Okay, now this is the phase space the distribution function, and if I integrate this f over d3p, I'm going to forget about factors of 2 pi and all. This basically gives me the number density as a function of x. Okay, and f obeys an equation. F obeys an equation, which is the Boltzmann equation. This you can actually derive quite explicitly, starting from classical mechanics or classical particles. Doing so for quantum mechanics is a little bit harder, but possible. So we will just say that all of this is classical, and the equation looks something like this. Forget about an expansion of the universe for the time being. Del T plus velocity dot del x. Let's say that there are no external forces for now. Acting on F is equal to something on the right hand side. I will write what that thing is later on. What this is should be familiar to us from Liouville equation in classical mechanics. The del t is just the time derivative. It says how it's evolving in time, partial derivative in time. And what this says is that in any given volume, at what rate are particles leaving? So the change in x, del x, is multiplied by the velocity with which these particles are leaving that volume. Right? And this is equal to something on the right hand side. So suppose there are no interactions, no nothing, just particles are just sitting there, inert gas in a box, not expanding. This is just zero. Okay. But we live in an expanding universe. So we have to modify this equation a little bit. What happens is that, first of all, I don't necessarily want to always deal with the phase space distribution function. I can take an integral of this equation with respect to d3p, and what that will do is it will convert the f to an n. So I'll get del t plus v dot del x of n is equal to 0, still not expanding universe. universe. It just says that particles go out of some volume into some other volume depending on their velocity. So just do integral d3p. In an expanding universe, what should happen? So this also should be familiar to you as d by dt. The total time derivative of the number density is 0. Basically says that in a closed box, number of particles is not changing. But if the box is expanding, what should not be changing is not the number density, but the total number. So in fact, what must happen is that d by dt times n times v is a constant, if let's say v is a function of time. And in the expanding universe, this equation basically boils down to d by dt plus 3 times a dot by a. A is the scale factor in FRW. This you can in fact write as the Hubble very easily. There are various ways of doing it. This is also the same thing as saying that d by dt of, I think, if I'm not totally mistaken, is equal to 0. Okay, the A cube is one co-moving volume. So you compare this A cube with the V. So this is the equation. So dn dt plus 3hn equals to 0. This is the equation for a non-interacting particle. Now, we can improve upon this. Let's say the particle has some interactions. What kind of interactions? Let's say that we are talking about dark matter. And the dark matter has interactions of this kind. That two X particles can annihilate into, let's say, two standard model particles. Let's call it S. And there is some cross section for that, sigma. Now, you remember I did an integral with respect to d3p. So on the right hand side, in the original Boltzmann equation, what appears is f1, f2 minus f3, f4, right? That's what appears on the right hand side of the Boltzmann equation. So when I do these integrals over d3p1, d3p2, multiplied by the cross sections, they will lead to some object which involves moments of this sigma over this d3p1, d3p2. That I will not derive that, but let me just directly write down what that quantity is. So what appears is a quantity which is called the thermally averaged cross section. This is actually rate per unit density. This has the definition integral d3p1, d3p2, e to the power minus e1 plus 2 by t sigma whole thing divided by integral d3p1, d3p2, e to the power minus a1 plus e2t. Okay, this is the definition, okay, of sigma v. And then this equation becomes d by dt nx plus 3h nx is equal to minus the number density decreases by how much? Something proportional to this rate times the nx. You see, this object has the dimensions of gamma, a rate, 1 over time. But you see, this has to be also proportional to the number of dark matter particles in the first place. So this is just the annihilation rate. But on top of this, there is also some production rate. So there is some number of particles, that nx particles that can be produced from the path. And that gives this extra contribution. So you can derive this equation. This is the equation that one needs to solve in order to find the relic density of dark matter. Okay. Now, there are different ways of solving it, as I said. Let me not do the algebra for it, because otherwise we will not be able to do anything to do with structure formation. Let me just tell you what the story is. If you look at this equation, you will find that initially n a cube, nx a cube, it falls like this, and this is the equilibrium solution, and then it departs and goes like this. The way to solve the equation is to say that, well, nx is equal to n equilibrium times some small departure early on, and you solve for small delta. That's one step. So that's, let's say, up to here. And then later on, what is happening is that this equilibrium solution is much smaller than nx. So the second part of the solution, which is here, you make the approximation that nx is much, much larger than n equilibrium. So this term, this last term actually goes away, and you can solve the second part. And this joining is done at some value in between. This often, instead of time, what is plotted is 1 over temperature normalized by, let's say, the mass of the dark matter particle. And this x is that variable, x is equal to m over t. And you join these two solutions and you get the final density. So I'll write down this answer. So if you do that, you will be able to find out what the number density is. And that number density leads to omega h square of 0.12 when this transition roughly happens, this transition x star, I will call it, roughly around 20. It depends on the number of degrees of freedom in the universe, so roughly of order 10. And the cross section, average sigma v, of the order 2 times 10 power minus 26 centimeter cubes per second. Okay. The one point that I would like to make here is that this x star is not where gamma is equal to h. Now this is the mistake that is made in many places. In fact, this is the place where the solutions are joined. If you strictly calculate x using gamma is equal to h, you will find that it is somewhat larger. So this formula that you find everywhere, the x that appears here, is not where gamma is h. That only works if you are going to make this very drastic approximation that it was following the exact equilibrium curve until this point, and then it just freezes out directly. But that solution is not correct. If you want to be correct to, let's say, 5%, that's not what you are supposed to use. So here, this formula is correct, and the x that enters here is the joining point. So you choose delta something to be order of 0.5 or so. And that's how you determine x star. Okay, so I will not go into more details of this. This is thermal freeze out. Okay, so this is done, and of course, as I showed you, the omega h square is inversely proportional to sigma v average. And so if you have strong interactions that lead to dark matter annihilations, the actual abundance is very small. If you have weak interactions, you tend to get the correct abundance. This is a plot from long ago, so 0.11, but now it's 0.12. Okay. There are further details that one can look at, in particular dependence on how G star varies with time, and all of this is done. You can look up the references, perhaps not the most interesting thing to do in a pedagogical lecture. A second idea for formation of dark matter is the exact opposite thing. It's something called freeze in instead of freeze out. Here, initially there is no dark matter. Dark matter is created out of, let's say, the decay of some particle. Let's say some B goes to XX. Okay, and it has some rate gamma. Okay, now then what will happen is that very early in the universe, you will create slowly some amount of this X particle, and then eventually this particle B will go out of equilibrium because the number density of B that exists goes as e to the power minus mb over t. So at some temperature where the universe temperature falls below the mass of this source particle, my production gets cut off, and then I freeze in to some particular density of dark matter. And this is called freeze in production. Again, I think I would like to skip it. Rather, I want to move on to structure formation. Okay. All right. So, any questions up until this point?
Okay, there is one question right now from Snehashis. Is there a physical significance of X star in the freeze out scenario in terms of decay or expansion rates then?
Is there some physical significance of H star?
X star.
X star.
Yeah.
This object that appears here?
Yes, I think so.
Yeah, I
Yes.
see. The way I would say it is in the precise derivation of this formula that you're seeing on screen, X star does not have a physical significance. It is just a mathematical device that you use in order to compute the two branches of the solutions. There is a very closely related value of X, which I will call X decoupling, where gamma is equal to H. But this particular formula that is used everywhere and shown everywhere, the X that appears here is not the one where gamma is H. But it's very close. It's very close.
There is one question from Raghu. Can you clarify if time when gamma equals to H is before or after X equals to X star?
Absolutely. Absolutely. See, gamma is equal to H is roughly the point after which abundance does not change at all. Okay, so let's look at this green curve here. That's roughly, let's say here. Here it becomes flat. The y-axis has a very big log scale. So from the point here to here, you can see the abundance is actually decreased by about an order of magnitude or even more. Okay, why is this happening? This is happening because by the time decoupling happens, my my abundance curve is no longer mm, tracing the Maxwell-Boltzmann distribution. It is already away from it. Whereas this point that I am talking about, maybe even this one, where I join the two solutions. So first I solve this part using one approximation, and then I solve this part using another approximation. This some point in this vicinity, this is what I would call X star. Whereas this point is what is X freeze out or X deck. So X freeze out is after X star, which is larger values of X. Okay. All right, let's move on to structure formation. The main point. Yes.
Basudeb, one more request from the admin. They're saying that your audio is breaking a bit. So if you could switch off the video or something to save some bandwidth, because they're recording the lecture. Yeah.
Sure.
Thank you.
Let me just see how to do that. Stop video. Should work. Okay, good. All right. Let's do the last part. Sorry, I'm really out of time. I wish I had a bit more time to do this. So the two-point correlation function of densities carries information about the nature of dark matter. So this plot that I had just shown you before, this P of K, this actually I can define now precisely, so there is no confusion. So P of K is basically defined by, let's say, let me do this, times 2 pi cube delta function of K minus K prime is equal to the average of delta K delta of K prime. Okay, if you want. This is it. This is the definition of P of K. Okay, heuristically, the way to remember it is take two positions, let's say 0 and x, compute average, do Fourier transform. Okay, this is roughly what will give you P of K. All right. Now, this is the object which has this particular shape. Indeed, the peak appears at k corresponding to k equality, and that is the scale on which p of k is maximum. So, in some ways, we would say that the two-point correlation function has maximum weight at this particular k. Now, of course, depends on how you normalize. You can multiply by powers of k, just define something else, and then you will lose the peak. But with this definition of p of k, at this value of k is when you have maximum two-point correlation function. Now, the two-point correlation function has this particular shape that I just showed you. It tends to have departures from this nice form that I showed you at, let's say this is k equality. In this region, especially, if you change the nature of dark matter. See, the P of k is very well measured in this range, up to about, let's say, a megaparsec or so, up to about k of MPC inverse. This is very well measured. So theoretical ideas that change the power spectrum at that scale are already ruled out. So all existing theories will lead to changes in the power spectrum here. And what is being plotted here is, as a function of k, the P of k in a given model divided by the fiducial P of k in cold dark matter models, which is what this curve would be. Okay? And in some models you can see that there's less power at small scales. In some models there's an oscillatory cutoff of this power. And this is something that one can understand. There are two ways, or three ways, if you will, that one understands these things. First is using this theory of spherical collapse. The idea is that you take some overdensity up to some radius, let's call it r, okay? And then you can solve this equation for this r, which is just the Newton's equation, and this mRT is simply saying that how much mass is there in this part of the volume. So Gm less RT divided by r square. This is the differential equation that one can solve. And what happens is this radius of this overdensity that changes with time. In an expanding universe, this radius first increases and then it starts collapsing. Okay? So these are things that are done routinely. You can, for example, follow Kolb-Turner, where this is done very nicely. Main important thing to know is that it starts collapsing roughly when the overdensity has some value that looks like 1.68. Again, these are numbers that you will see often in cosmology papers. It's useful to understand where they come from. They come from, this number is computed in the specific case of spherical collapse, but then is used fairly generally, even where spherical collapse is not exactly applicable. Okay, so I stole these slides from my good friend Asim Paranjape, who's the expert. But main point I want to make here is that there is this simple theory called spherical collapse, which you can solve analytically. But in most cases you can't. In most cases you can't. And what you have to do is perturbation theory. Okay, so what you say is that we had started with F. From F we could go to number density, energy density, and so on, and pressure even. And you write down fluid equations for these objects. Okay, so there are three equations that need to be written down: the continuity equation, the Euler equation, and the Poisson equation that talks about how much gravity is affecting things. And a whole bunch of approximations later, in the most important of which is saying that rho, let's say for matter, is some rho bar times 1 plus, let's say, delta. So this is the average density, the homogeneous solution to the problem. And then this object is in real space. You take its Fourier transform, you'll find that if you linearize in things like this over density, this linear equation, even if it's a partial differential equation, can be converted to a independent equation for each Fourier mode corresponding to, let's say, some spatial scale x, now in co-moving scales, which looks something like this. And this equation is nice and easy to interpret. Basically, if you for just a second forget about this term, which talks about Hubble expansion, it says that the second derivative of something is equal to some, that same thing multiplied by the term in the brackets. So this is a harmonic oscillator. Okay, if this term in the brackets is negative overall, That says that you will have oscillatory solutions. If this thing is positive, you know that there are exponential solutions. Okay, so you have growing or decaying solutions depending on which of these two terms is larger. This term corresponds to the effect of gravitational collapse. And this term is because of pressure. Okay. And so when this term wins, basically everything collapses. That's an exponential increase in the over density. When this term wins, it basically means that pressure counteracts gravity and you set up waves. What this term does is it stretches the box and essentially leads to a friction-like behavior. Taking different limits of this equation for different, time dependencies of the scale factor will then show you how delta for a given species evolves as a function of time. That's one way of solving these problems. And finally, there is the method of in-body simulations, where you take a bunch of particles and you simulate their trajectories, starting with some initial conditions. And basically, you apply Newton's laws to each of these particles, F equal to ma, for the particles that are nearby, and the ones that are far away contribute in some average sense. There are many, many details and many subtleties associated with these calculations. Perhaps, again, I'm not the expert and not the time to do this, but it's important to know that once delta becomes order 1 or larger, order let's say 0.3 or larger, it becomes important to use these numerical techniques. You can't do very much analytically. So if you apply a variety of these techniques, spherical collapse, linear perturbation theory, and then finally n-body, you can find out um, for different dark matter models what your P of k looks like. And suppose you go and measure the power spectrum, you would be sensitive to these things, except of course that on these very large values of k, which corresponds to very small length scales, nonlinearities are important, and so you might not be able to directly measure P of k, unless if you go to very high redshift, let's say. Rather, you might be more sensitive to other objects, like say how many halos of a given mass are there, how many objects of a given mass are there, and so on. So these are important subtleties and details. But the main point to take away from this discussion is that dark matter properties affects the way in which dark matter clusters, and the way in which dark matter clusters can be computed using these different techniques. And then you can go and compare with data just by measuring, let's say, two-point correlation functions, using in observations or counts of various objects with different masses, and so on. Okay, so I think I am out of time, but if the moderators permit, maybe a couple of questions.
Okay, so there are a couple of more questions, maybe if you would like to take. So one is from Sunil Malik. If one consider the baryon dark matter interaction, what would be the modification to the linear perturbation theory?
Good question. What it would do is it would add to the pressure for dark matter. So dark matter has some equation which, let's say, looks like this. If you couple dark matter to baryons, which are then interacting with photons, let's say, or the other things going on there, what it would do is it would, at least on small scales, okay, two things will happen. Baryons will kick around the dark matter particles, and in principle it can make the dark matter structure more fuzzy, so the less structure. On the other hand, dark matter also has the ability to lose energy by just emitting photons and collapse into very tight objects, and in doing so it can drag the dark matter with it. Which of them wins depends on the exact circumstance, but if I have to give a simple answer, the simple answer is simply that uh, there will be additional pressure for dark matter.
Uh, there is a question from Subinoy. This
Mhm.
oscillation in small scale gets erased by nonlinear evolution. Is 21 centimeter or high redshift observation, whether these can detect these oscillations?
Indeed, indeed, indeed. That's a very good point. In fact, I might have even mentioned it, that this picture that I'm showing, the Ks are very large. These Ks correspond to scales that are completely nonlinear now. So you will not be able to measure this power spectrum just by going and counting galaxies or whatever. But if you're looking at some redshift of say 5, then the effective scale of nonlinearity is shifted in such a way that in principle at least some part of this could come in the linear regime, and then you might be, let's say, using Lyman alpha, you could be able to measure the linear power spectrum at these nonlinear scales. I don't know of any. I mean, okay, I'm not aware of detailed proposals in this direction, but okay, one can find this out. I don't remember any references directly.
Okay. So there is a question from Professor Patrick Dasgupta. If there is a small rotation in the dark matter over density, what would be the collapse like?
Ah, hmm. So you want to give the dark matter some overall, angular velocity, so that it resists the collapse a little bit. Is Yeah, in principle, that would so for sure this is known that in primordial black hole formation, um, if you have angular velocities of dark matter, that would raise the threshold for PBH formation, which means that collapse becomes more difficult.
Okay, since we have run out of time, so we end this session here, and I think a lunch break would follow. Thank you, Vasudevda, for
Thanks a
the
lot.
exciting talk.